Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be learning about reflection of light waves. So relax, do not go anywhere, I will be right back. You are welcome back to my school YouTube channel. Like I said earlier on, we shall be learning about reflection of light waves. But remember, in our previous video we did the part 1. So today we are going to be doing the concluding part, which is the part 2. Okay, so before we begin with our lesson, let's quickly run through the objective for today's video. So number 1, at the end of the lesson, scholars should be able to draw array diagrams to show the formation of images by plane and curved mirrors. Then 2, explain some practical application of these mirrors. So let's begin with our lesson. So here we are going to be discussing about image formed by a plane mirror. Now remember, this is a continuation of our previous video. Okay, so we have done the preliminary or the introductory part of reflection of light waves. Okay, so now let's start. How is a plane mirror formed? So basically that's what we are going to be talking about in this first slide. So a plane mirror is produced by simply coating one side of a plain glass sheet with silver, right? So the silver coated sides prevent light from passing through the glass, but the light rays are reflected. Okay, so below is the diagram of image formed by a plane mirror. Okay, so as you can see, this is the object, okay, and this is the head of the object labeled O. Okay, then we have the image formed behind the mirror. So this is also the head of the image formed. Then from what you can see from this diagram, you can see that 2 light rays are incidented on the plane mirror. Okay, and these are reflected, okay, as C and D. Right now, if you produce these 2 rays backward, it's going to meet the image at the end. Okay, but then there's another image again that is incidented from the head of the object to the plane mirror. Now this ray is not reflected, so we just produce it, okay, to meet. So after producing it, you discover that it's going to meet the previous 2 rays, okay, that we also produced. So as we move to the next slide, you will really explain how this works. Okay, so let's move over to the next slide. So this is just a description of what is happening in that diagram that I was trying to explain. So the object O is placed in front of the mirror, like we saw in the diagram. 2 incident rays, OA and OB, from the head of the object strikes the mirror at A and B, and these rays are reflected as AC and DC respectively. Of course, when I was showing you the diagram, I did mention all this. Now, the reflected rays appear to the observer at E, which is that eye you saw in the diagram, as if they are coming from I. Okay, so the reflected rays appears to the observer at E as if they are coming from I, but in reality, they are not coming from I. Okay, so I is the head of the image form. Of course, I showed you that. Now, when rays AC and BC are produced backwards, they meet at I. Now, there's another ray. A ray ON, normal to the mirror, is reflected back along ON, and when produced, it meets the other 2 at I. Now, since no ray actually comes from I, okay, so there's no ray coming from I, the image only appears to be there, okay, but it is not actually there. So that image that was formed in that diagram, can we go back to the diagram, please? So that image, this image that you are seeing here, only appears to be here, but in reality, it's not really there. And the reason is because these rays only look as if they are coming from the image, okay, but they are not coming from the image. So let's go back to the previous slide. Okay, so since no ray actually comes from I, that is, no ray is coming from the image only appears to be there, but it is not actually there. So this kind of image is called virtual image. Okay, so a virtual image has no real existence. Okay, even though it can be seen, it has no real existence. So let's move to the next slide. So on the next slide, we are going to be talking about that virtual image and real image. So what is a virtual image? So a virtual image is one through which light rays do not actually pass, okay, but that virtual image is still visible to the human eye. So the human eyes can see virtual image, but light rays, okay, does not pass through them, right? So a virtual image cannot be caught on a screen, okay? And example of virtual image is the image produced in plain mirror. Okay, it's an example of virtual image. Then we have another type of image called real image. So the real image is just the opposite of the virtual image. So the real image is one through which light rays actually pass. Okay, and a real image can be caught on a screen. And a good example is the image produced in a pinhole camera. Okay, so a pinhole camera produces a real image, whereas a plain mirror produces a virtual image. So let's quickly run through the characteristics of plain mirror images. So the following are the characteristics of the image formed by a plain mirror. One is that it is same size as the object. So the image formed by a plain mirror, okay, and the object, both of them have the same size. So let's take, for example, let's say, of course, here, when we are talking about size, we are actually talking about height. Okay, so let's say the object has a height of 6 centimeters. Then the image formed, okay, will also have a height of 6 centimeters. Okay, so number two, it has the same distance behind the mirror as the object in front of the mirror. Okay, that is image distance from mirror equals object distance from mirror. So for example, if you place an object in front of a plain mirror, let's say 2 centimeters from the plain mirror, right? Now the image formed will also be 2 centimeters behind the plain mirror. So both of them have the same distance from the mirror. Okay, so let's move to the next slide. Now, it is virtual. So when we say something is virtual, we've already defined that before. So we are saying it is not real. That is, it cannot be caught on the screen, okay, and light ray cannot pass through it. Okay, then 4, it is laterally inverted. Okay, so when we say it is laterally inverted, we are simply saying that the left hand is seen as right and vice versa. Okay, so let's say, for example, an object is in front of the mirror, right? So the left hand of the object is going to be the right hand of the image produced by that mirror. So that is exactly what IV is saying. Then it is upright. Okay, for example, if I'm standing in front of mirror and I'm standing with my leg, in my image, okay, in the image produced by the mirror, I'm also going to be standing with my leg. Okay, that's what we mean by upright. So sometimes we may use the word erect. Okay, they are still the same thing. So these are the characteristics of images formed by a plain mirror. Now let's talk about inclined mirror. So sometimes mirrors can be inclined, okay, at an angle. So when two mirrors are inclined at an angle to each other, a number of images are formed depending on the angle of inclination between the two images. Okay, so to calculate for the number of images formed by an inclined or by inclined mirrors, we simply make use of this formula. N is equals to 360 over theta minus 1. Okay, where n stands for the number of images and theta stands for angle of inclination of the mirror. Let's move over to the next slide so that we can apply that formula in solving some problems. So let's start with question A. Two plane mirrors are inclined at an angle of 20 degrees to each other. Determine the number of images formed when an object is placed between them. So remember the formula for calculating the number of images formed by a plane mirror, and that is n is equals to 360 all over theta minus 1. So in this question, we're actually looking for n, which is the number of images formed, but we are given theta, which is the angle of inclination, to be equals to 20 degrees. So applying the formula, we'll be having n is equals to 360 all over theta minus 1. But remember, in this question, theta is equals to 20. So in place of theta, we replace it with 20. So 360 divided by 20 minus 1, and that will be, of course, 360 divided by 20, that will be equals to 18. Then 18 minus 1, that will be equals to 17. Okay, so therefore, the number of images formed, okay, when an object is placed between those two mirrors that are inclined at 20 degrees to each other, is equals to 17. Okay, so let's see example 2. Now, two plane mirrors are inclined to each other such that an object placed between them has 11 images. Determine the angle of inclination. So most times in physics questions, I think basically you just have to arm yourself on how to perform change of subject or formula. So if you can manipulate change of subject or formula, you should be able to solve a lot of the questions. Okay, for example, the first question that we just solved and the second one that we are going to solve, we discovered that we just use a single formula. We did not come up with any other formula. Of course, some questions in physics, you may as well need other formulas to be able to solve a particular question given to you. But for this one, okay, we don't need any other formula apart from the inclination formula. Okay, so here in this question, we are given n to be equals to 11, and we are asked to determine the angle of inclination, which is theta. So we still apply the same formula, which is n is equals to 360 all over theta minus 1, right? So in place of n, we replace it with 11. Then we still have our 360 all over theta minus 1. So the next thing to do is to move our minus 1 to the other side of the equation, so that we'll now be having 11 plus 1 is equals to 360 all over theta. Of course, we are looking for theta. So theta and 12 can switch position. So theta move to the position of 12 and 12 move down to the position of theta, of course, or you can go cross multiply. So if we cross multiply, we are going to be having 12 theta is equals to 360. Now we are looking for theta, so we divide both sides by the coefficient of theta, which is 12. Okay, so that theta is equals to 360 divided by 12, and that will be equals to 30 degrees. Okay, so the angle of inclination between the two plane mirrors is equals to 30 degrees. So let's move over to the next slide. Okay, so we also have another question, which is example C. So an object 8 centimeters in front of a plane mirror moves at a speed of 6 centimeters per second away from the mirror. What will be the distance separating the object and the image after 2 seconds? So to solve this question, we'll have to move over to the board to provide answer to this question. So for this question, I think it's necessary for us to draw diagram. But if you don't want to draw the diagram, no problem. Okay, but drawing the diagram will kind of serve as a guide. Okay, so in this question, we are told that, first of all, let's draw the mirror. So let's say this is our plane surface, our horizontal surface, and this is the mirror. Okay, so let's say this is the non-reflecting surface of the mirror, and this is the reflecting surface. So we are told that an object is placed 8 centimeters. So let's say this is the object, let's say it's a person, and the distance, okay, between the object and the plane mirror is 8 centimeters, right? And we are told that this object moves at a speed of 6 centimeters. So speed equals to 6 centimeters per second. Then we're also told that it did that for 2 seconds. Okay, so here we have 2 seconds. So now from here we can calculate the distance. Okay, the object actually moved away from the mirror. So remember that speed is equals to distance all over time. So we know speed to be equals to 6 centimeters per second. Distance we don't know, but time we know. So since we are looking for D, we just cross multiply, right? So if we cross multiply, we're having D to be equals to 12 centimeters. So this object move away from this 8 centimeter point another 12 centimeters. Now the new distance between the object and the mirror will now have to be 12 plus 8, and that will be equals to 20 centimeters, right? Now, but remember that in this question, we are asked what will be the distance separating the object and the image. Now, remember when we were talking about the characteristics of images formed by a plane mirror, we said the object distance, that is, the distance separating the mirror and the object, is also equal to the distance separating the mirror and the image, right? So if now in this case the distance separating the object and the mirror is equal to 20 centimeters, that means the distance separating the image, okay, so let this represent the image. So the distance separating the image and the mirror will also be 20 centimeters according to the characteristics of images formed by plane mirror. But remember, in this question we are asked to calculate, to find the distance separating the object and the mirror. So for us to find or to calculate the distance separating the object and the image, we will have to add the distance between the object and the mirror to the distance between the mirror and the image. Okay, so if we do that, we'll be having 20 centimeters plus 20 centimeters, and that will be equals to 40 centimeters. Therefore, the distance separating the object and the image is equals to 40 centimeters. So let's return back to the screen to continue with our lesson. So here we are going to be talking about the application of inclined mirror. Okay, more or less like the uses of inclined mirror. So one of them is in your kaleidoscope. Okay, so the kaleidoscope is a toy which uses the principle of inclined mirror to produce multiple images. So it consists of a tube in which two mirrors are fixed and inclined at 60 degrees to each other. So we have another place where inclined mirror finds application, and that is your periscope. Okay, so the periscope is an instrument used to view over barriers or obstacles. They are used by soldiers in armored tanks. So a simple periscope consists of two parallel plane mirrors facing each other and inclined at 45 degrees to the walls of periscope tube in which the mirrors are fixed. So the object is viewed over the barrier. Okay, and another application of inclined mirror is in the sextant. Okay, so sextant is a device, okay, or is an instrument used by navigators to measure the angles between the sun, okay, and the horizon, right? So those are the applications of inclined mirror. So let's move to the next slide. So on the next slide here, we are going to be discussing about mirror rotation. So when a mirror is rotated, what happens? Okay, so if the incident ray has a constant direction and the mirror rotated through an angle theta, the reflected ray is rotated through angle 2 theta. So this diagram is just a depiction of what I was trying to say. So this is the mirror SY, this is the initial position of the mirror XY, then the mirror is now rotated at an angle theta. Okay, so we now have a new direction which is UV. Okay, so basically here we just want to prove, okay, that arrow 1 and arrow 2 is equals to 2 thetas, right? It's equals to 2 theta. So first of all, let's describe this diagram. Okay, so from this diagram we can see that Ni is the incident ray. Okay, Ni is the initial incident ray, so take note of that. While N1 or N1N, whichever direction you want to follow, is the normal. Okay, while N arrow 1 is the reflected ray. Okay, so let's go ahead and describe this. So N1 is the, okay, IN is the incident ray at angle I on the mirror SY, which is the initial position of the mirror before it was rotated at N. So N1N is the original normal, which is what I've shown us, which is here. Then arrow 1N is the original reflected ray. Now remember here, therefore, angle IN1 is equals to, is the angle of incidence. That is NIN1. This place represents the angle of incidence. Now remember that the angle of incidence is the angle between the reflected ray and the normal. So this is the normal and this is the reflected ray. Okay, so that angle is equals to I. So let's move to the next slide. Now also arrow 1 N1 is equals to arrow, okay, which is the angle of reflection, which is also equals to angle of incidence, and that is according to the second law of reflection. The angle of incidence is equal to the angle of reflection. Now with the mirror rotated to position UV, through angle theta, the normal is also rotated. So take note of this. When the mirror is rotated through angle theta, the normal itself is also rotated through theta, and the new normal becomes n2 n1, and the new refracted ray becomes arrow 2 n. So please, let's go back to the previous slide so that we can see this. So this is the new normal, n2, and this is the new reflected ray, okay, n arrow 2. Okay, so let's return back, please. Okay, so now angle n1 n2 is equals to theta. Now by law of reflection, angle in n2 is equals to n2 n arrow 2, which is equals to I plus theta, right? Then angle n2 n arrow 1 is equals to I minus theta. But the angle through which the reflected ray rotated is equals to arrow 1 n arrow 2. So here we'll be having n2 n arrow 2 minus n2 n arrow 1 to be equals to I plus theta, then minus I in bracket minus theta, all in bracket. So if we open up this bracket, of course this minus is going to multiply I, so that we'll be having minus I. Then this minus will multiply minus theta to give us plus theta. Okay, so I will cancel out I because this I here is positive and this is negative. So if we bring them together, they are going to cancel out. So that at the end of the day, we have theta plus theta, and that will be equals to 2 theta. Okay, so the essence of this is just to prove that the new rotated angle, or the new angle of reflection, is equals to 2 times the angle of rotation. Okay, but just take note of that. So when a mirror is rotated through an angle, the new reflected ray is equals to 2 times that angle of rotation. So basically that is what I'm trying to show here. Okay, so let's move to the next slide. So in summary, the angle of incidence before rotation is I, or ni1. The angle of incidence after rotation is now I plus theta, or in(n)(2). Then the angle between the initial normal n(n)(1) and the final normal n(n)(2) is equal to the angle of rotation. Okay, then the angle of reflection before rotation is arrow, or arrow 1 n(n)(1). Now remember that all these angles we are mentioned. For example, this angle of reflection, take note that the angle of reflection is the angle formed between the reflected ray and the normal. Okay, so that's why you are having 3 letters here, arrow 1 n(n)(1). Now the angle of reflection after rotation is I plus theta. Of course, that is because this is in accordance with the second law of reflection, right? So if, okay, this is in accordance with the second law of reflection, and that is arrow 2 n(n)(2). So the reflected ray is rotated through twice the angle of rotation, which is 2 theta, or arrow 1 and arrow 2 as shown in the diagram above. Now the angle between the normal after rotation and the initial rotated ray is I minus theta if angle of rotation is less than the initial angle of incidence, or theta minus I if angle of rotation is greater than initial angle of incidence. So basically what I want you to take note of is which is this point 2. So the reflected ray is rotated through twice the angle of rotation. I think that's the most important part, and this also. So let's move over to the next slide so that we can apply what we have just said in solving some problems. So let's begin with question 1. A ray of light is incident on a plane mirror at an angle of 20 degrees. This mirror is rotated through twice this angle. In this new position, the angle between the incident ray and the reflected ray is, so first of all, we are told that a ray of light is incident on a plane mirror at an angle of 20 degrees. Then this mirror is rotated through twice this angle. Okay, so from here we can actually get our angle of rotation, because our angle of rotation is not given to us, but the angle of incident was given. But we are told that the mirror is rotated through twice this angle. So from here, we just know that the angle of rotation is 2 times 20. So the angle of rotation is 2 times 20, which is 40 degrees, right? Now in this question, we are asked to find the angle between the incident ray and the reflected ray. Okay, now remember that the new angle of incident, okay, is I plus theta, right? Then the reflected ray is also I plus theta. You get? So if we add these two together, since we are looking for the distance between both angles, so if we add these two together, definitely we are going to be having 2 brackets I plus theta. The angle between the incident ray and the reflected ray is giving us 2, then bracket open, I plus theta. Okay, so that is where this formula came from. So we already know our I to be equals to 20, and we know theta to be equals to 40. So we just plug it into this formula. So in place of I, which is the angle of incident, we replace it with 20. Then angle of rotation, which is 40, we replace this theta with 40. So 20 plus 40, that will be equals to 60. Then 60 times 2, that will be equals to 120 degrees. Hence, the angle between the incident ray and the reflected ray is equals to 120 degrees. So let's solve example 2. An incident ray is reflected normally by a plane mirror onto a screen where it forms a bright spot. The mirror and the screen are parallel and 1 meter apart. If the mirror is rotated through 5 degrees, calculate the displacement of the spot. So in order to solve this question, let's move over to the board. Okay, so first of all, to solve this question, it is necessary for us to make a sketch of the mirror. Okay, so this is the mirror, and now remember that we are told that the screen and the mirror, they are parallel. So let's take this as the screen. Okay, and we are told that the distance between them is 1 meter. Okay, now remember that in this question we are told that an incident ray is reflected normally. Okay, so when an incident ray is reflected normally, we are just saying that the angle of incident, okay, and the normal, they all lie on a straight line. Okay, now remember that your normal is straight, right? And then the incident ray is reflected normally. So that means that reflected ray is going to form an angle 90 with the mirror. Okay, so this is where the spot will be, right? So when this mirror is rotated, then the spot is going to move a little. So this becomes the new reflected ray, right? But remember that this becomes the new position of the spot. But remember that, okay, the angle of reflection is equals to 2 times the angle of rotation. So in this case, we are told that the mirror is rotated through 5 degrees. So that the angle of reflection, okay, R will be equals to 2 times 5. That will be equals to 10 degrees. So the angle here will be equals to 10 degrees. So in this question, we are asked to calculate the displacement of the spot, which is the distance from the initial position, okay, of the spot to the new position of the spot. So we can call here I, right? Now if you look at this line, this distance and this, both of them are parallel. Okay, so that means here is also 1 meters, right? So since we are looking for here, and we know that this is our opposite, and this is our hypotenuse, and this is adjacent. So in that case, we are going to be making use of tan. Okay, so tan theta is equals to opposite all over adjacent. Remember your SOHCAHTOA, SOHCAH, then TOA, opposite over adjacent. So here, theta is equals to 10 degrees. So here we're having tan 10 is equals to, then the opposite is x, and this is 1. So we cross multiply. So here we'll be having s is equals to tan 10 times 1, okay? And tan 10 is equals to 0.176. Okay, so 0.176 times 10 is still the same thing as 0.176 meters. Okay, so the displacement of the spot when the mirror is rotated is equals to 0.176 meters. Of course, this we can convert to centimeters, right? So to convert from meters to centimeter, we simply multiply by 100. So if we multiply 0.176 by 100, we'll be having 17.6 centimeters. Okay, so in centimeter, the displacement of the spot is equals to 17.6 centimeters, but in meter is equals to 0.176 meters. Okay, so let's return back to the screen to continue with our lesson. So let's solve example 3. A ray of light is incident normally on a plane mirror if the incident ray is kept fixed while the mirror is rotated through an angle of 30 degrees. Let's move to the next slide. Determine the initial and final angle of reflection respectively. So whenever a ray is incidented normally, okay, on a plane mirror, it simply means that that ray, okay, and the normal are all lying, okay, are all lying perpendicular to the mirror. So in that case, the angle of incidence in this case is going to be 0, and the angle of reflection is going to be 0. Remember the second law of reflection. Okay, so let's provide answer to this question. So this one, I just put it here so that you just take note of it. Okay, so when a ray of light is incident normally on a plane mirror, it simply means that the ray of light strikes the mirror at a 90-degree angle. Okay, that is perpendicular to the surface of the mirror. So in that case, angle of incidence will be equal to 0, and angle of reflection is also going to be 0. So just take note of this word, incident normally. Is very, very important. Okay, so now we are asked to determine the initial and the final angles of reflection. So from what we just said now, the initial angle of reflection will be equals to 0. Since the angle of incidence equals to 0, then the angle of reflection will also be equals to 0. Take note, this is in accordance with the second law of reflection, right? Now, the final angle of reflection will now be equals to 2 times the angle of rotation, okay? And the mirror is rotated through 30 degrees. So 2 times 30, that will be equals to 60 degrees. So therefore, the initial and final angle of reflection respectively are 0 degree and 60 degrees respectively. Okay, so this is where we draw the curtain for the preview of today's video. I believe you enjoyed it. You can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, we talked about the types of curved mirrors and we explained them. We also talk about their uses. Okay, we also discuss about the terms used in spherical mirrors. Then we also talk about the mirror formulas and how to adhere to the sign convention when using these formulas in solving problems and many more. I believe you enjoyed the preview of the video that you've just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.